So when we ask for the electronics configuration, we have to do it the way you teach us, not just look it up from the predict table and put it in.
Well, I mean, hopefully I'll ask a slightly more clever question than just look at the periodic table. I'm just saying you can use that. That's sort of one of the advantages that one of the only advantages we have, sort of doing this remotely. That is, if I was giving you a test, you'd have to come up with it on your own. So I'm going to try and since you have access to your computer and your phone and whatever else, you just be able to look it up. So what I want you to do is really understand I'll ask you questions about it, if you truly understand how the electronic configuration, where it comes from, how it relates to other elements. One of the questions we have on the recitation today is about ions. Now, when we can think about ions aren't going to have the same amount of electrons as the elements do by definition. Mm-hmm. So they will have a different electron configuration. And so the idea is, do we understand why did they have a different electron configuration? And secondly, why is that electron configuration more stable than the electron configuration of the element itself? Why do they become ions in the first place? These are things that I want people to understand more than just memorizing the electron configuration. So that's like I said, things you can look them up. I want you to understand
the concept behind how we figure out,
that's
and
more
become knowledge for everybody.
Mm-hmm. Exactly.
25.
So, does anybody have anything they want to chit chat about before we get going? I have all the questions here, and so we can start wherever you like. I figure we might as well start with one, and we can go from there. Anybody have anything they want to check? Nobody's chatting.
We're ready to roll, Professor.
Apparently, I like. I think everyone's getting Zoom doom. They're just tired of looking at screens. Believe me, I get it.
Yeah.
But this is sort of what we're stuck with for now. So we'll try and make the best of it.
We're betting that. So.
Yeah. We'd certainly have a lot more fun. I was just talking with some of the students in the office hours the other day, how recitation and lab are two of the things that really suffer from being online, because students don't get to interact with each other. And especially in recitation, I've had students in the past who just did a fantastic job. What I try and do is I get students to work in groups of like 4 or 5. And there'd always be 1 or 2 in each group that would understand the concepts much better than the rest. And they would explain it to the other students. And that was great for a couple of reasons. One, you never understand anything as well as when you can explain it to somebody else. That is excellent. And 2, a lot of the time, dumb guy like me doesn't explain things the proper way. I talk over your head, or I talk past it, or I say things you don't understand. And the students get that, and they explain things I find much better than I can. And so we sort of miss out on that a little bit into these circumstances, unless you guys could meet. That's why sort of at the end of the recitation, I just leave the meeting and just let whoever hang out as long as they want, and sort of share ideas back and forth. Take advantage of that if you can. Because some of you are going to be much better teachers of this than I am. Hopefully, fingers crossed. And you may be there right now. You never know. So, yeah, we sort of miss out on that when we don't meet in person.
This is one of the big advantages about meeting in person and have a chance to learn from other students. Sometimes they get the point really delivered in short amount of time.
Mm-hmm. Not only that, but you find that when you finally understand something. And you may understand it in a different way than I do. Hopefully that will happen. You understand it on a different level than I do. And it's sort of, your brain opens up, and then you desperately want to share that with somebody. And a lot of times when you're learning something for the first time, looking at it from this perspective may not signal anything to you, but look at it from this perspective over here, that may be the one that sort of sinks in and goes, oh, and the light goes on. So having more than one perspective to explain things is tremendously helpful. Because, we've all had good teachers and bad teachers in the past. And sometimes the best teacher happens to be one of your classmates. You never know. So why don't we start here, and then you can go, and then we'll go through, and this will hopefully be fairly straightforward. And then as we go through, there'll be some new things we're going to pick up that we'll talk about next week. You sort of have a jump on the rest of the class. But a lot of this is going to be review. Some of it will be new, and hopefully it'll all make a little bit more sense by the end of the class today. So first one, very straightforward question. What are the 4 quantum numbers? And what are the possible values they might have? So remember, these are the numbers we're talking about, not just the letters. They want the numbers. So, and then you don't have to describe them. You don't have to say this one's principal and this one's magnetic or whatever. I like to think of them as shell, subshell, orbital, spin. Because that way I sort of understand what each one of them is. So let's start with the shell. What number is that? Or what do we call that? It comes with a letter. What letter do we call the first number, the shell, the principal quantum number? It has
Yep. So mine just mentioned it's S. So in the chat.
S is a subshell. S is a shape of one of the subshells.
Mm-hmm.
So yeah, Ryan's got it.
N1.
Ferris has got it.
Mm-hmm.
So what is
N1?
N? Yeah, the first one is N. So I like to think of the first one as the shell. That's just easy for me to understand. The shell is just how far away the electron is. And every time we fill a shell, we start filling another one. So the first one is N. What's the second one, the subshell letter? What do we call that? The first one is N. What's the second one? Again, Nick and Ryan to the rescue. Someone read it to me. If you read in the chat, what does it say?
L.
L. Now again, how do you N? Everyone sort of N. That's a common, stands for number. L, you can think of it as subshell or something. L is just N and L, and then the other two are orbital, which tells us. And remember, each time we go down, we're getting more and more information. So the first one tells us basically what level it's on. And then we get more information. We say what shape the orbital that it's in. And the third one, where in that orbital. Basically, it's the orbital address. Because we know there's a bunch of different ones. And there's a lot of different shapes. Which one is it? And then finally, it's the electron spin itself. So what's the number we give to or the letter we give to the orbital? Be a hint, it's 2 letters actually. Yep, Ryan's got it.
Ryan got it. I'm L.
So it's M, and then L is a subscript. And then finally, what's the last one? Is the spin. So as we go down, shell is a series of electrons, subshell, smaller series of electrons. The orbital means it's one of two electrons, and then the spin tells you exactly which electron it is. It's either this one or it's this one. It's either spinning in this direction or spinning in that direction. So the final quantum number tells you exactly which electron it is. We've narrowed it down to just one. Yes, Nicholas.
So ML and the MS is like the street and then the actual house address?
Sure. Yeah, if you want to put it that way. Yeah, N would be like the country, and L would be the, or I guess would be the state, and then L would be the city, and then orbital would be the street, and then the spin would be the actual number on it as we keep narrowing down and down, down and down. So yeah, M, so capital, well, not capital M, large N, S for spin. Now let's go over what these numbers can be, since the whole question is, what are the possible values they can have? So for shell, what number, that could be a series of different numbers. What's the lowest possible value it can have?
I can't remember.
Is it 1?
It's 1, yeah, because it tells you how far away from the nucleus it is. So this is my nucleus. The first shell is 1, and then 2, and then 3. So the very first one is 1. And then basically it goes out to, I think, 7? If I look at my periodic table. Each row on the periodic table is a different value for N as we go across. So each row is a shell. And so we have, let's look, we have 1, 2, 3, 4, 5, 6, 7. So 7 is the biggest one we have on the periodic table so far. So 1, 2, 3, out to 7. So that is the first quantum number, the shell, the principal quantum number, 1 to 7. Now, what values for L? How many different subshells are there? So remember, inside each shell, every time we increase a level, we add a new subshell. So then that stops when we get to a certain number. Nicholas.
I think Ryan said 4, but is that also, are we talking about the shapes? Is that the subshells, like the D, S, P, and F?
That's exactly what that is. Yes, the subshells are S, P, D, and F, and they have a letter associated with each one. And this is where it gets confusing, because I think people get confused between the shell and the subshell. The shell starts at 1. It goes 1, 2, 3, 4, 5, 6, 7. The subshell doesn't, though. What's the first number in the subshell? So L has 4 values that's associated with S, P, D, and F. So L can have 4 different values. What's the first one?
That's 1.
Is it 0?
It is 0. It is 0. And I'll try and think of a way that you can remember that. That's 0, which is S. P is 1, D is 2, and F is 3. So it's 0, 1, 2, and 3. And the reason why this is a 0 becomes apparent when we look at the next one, when we look at the orbital, because M to the L is based on L. It's actually based on the number that's in L. Now the orbital number basically gives you the information of how many orbitals there are inside each of these subshells. And remember, that m to the L can be any value between minus L all the way to plus L. Okay, that defines m to the L. So whatever L is, 0, 1, 2, 3, m to the L is negative that number, 0 to positive that number. That's why S is given the number 0, because how many orbitals are there in an S subshell? Nope, not 2, Nicholas. No subshell has 2 orbitals, actually.
Is the orbital what the electrons go in, like the little boxes?
Exactly. That's exactly what they are. They're the little boxes. So they either have
1
them like this. So they either have,
or
there's
3.
a certain number they have. So what's the smallest number of orbitals in a subshell?
Two electrons, is that what?
2 electrons. That's right. So there's the S subshell only has room
For
for
2.
2 electrons. So how many orbitals is that?
1.
1
1.
orbitals.
It only has 1. And because it's the L for the S orbital is 0, we can't go, there's no minus 0 and there's no plus 0. There's only 0. So the address, the orbital address for an S subshell is
1.
is 0. So if I have an m to the L of 0, that tells me it's either in an S orbital by itself, or it's in a p orbital in the middle, or it's a d orbital in the middle, or an f orbital in the middle. But because we keep expanding on one side and the other, that's why there's 1 orbital in an S, and then there's +1, +1, 3 in a P, and then plus another one on either side, 5 for D, and then plus another one, and plus another one on the other side for F. So for P, what are my possible? Yes, Nick.
Sorry, can you just clarify? So you're saying, if I'm getting it correctly, because it's 0, it has that many possibilities?
Well, 0 is the physical address. 0 is the physical address of that orbital. And since there's only 1, we give it the address 0. Because when we get to larger subshells with more orbitals, they'll have other values in addition to 0.
So like when you're saying that it could possibly be in the middle of P or possibly middle of D.
Right.
So
yes. So all subshells have a 0 orbital. They all do. Yeah. But with an S orbital, that's the only one it has.
Okay.
P has 2 more, and then D has 4 more, and then F has 6 more in addition to the 0 orbital.
Okay.
Yeah. So for S, it can only be 0. That's the only possible value it can have. Now, what about P, though? What are the
3.
possible values of P orbitals for m to the L?
I think 3.
And remember, this is the formula we use. So what are the possible values of m to the L for a p orbital? P subshell, sorry, P subshell. Yep, that's right, Ferris. You want to tell us?
Yeah, I was gonna say the same thing. Ferris typed. Yeah, he got it first. So -1, 0, and 1.
Right, because we go,
Isolate
because
pairs.
the value of L, so this is our L values over here for our different subshells. And it's either 0, 1, 2, or 3. So the value for P, since it's the second one, is 1. We start at 0, and then we go to 1. And then M to the L, which is the orbital inside that subshell, goes from, I'll get you in a second there, Nick, goes from minus L to plus L, all of the integer values in between. So since it's 1, we start at minus 1. And then we have 0, and then we have plus 1. So those are 3 different orbitals, and their addresses are minus 1, 0, and plus 1. So if we were to write an orbital diagram for P, so here's our, we're putting our electrons in it. The first one over here, we would say is minus 1. The one in the middle is 0, and the one on the far right is plus 1. It actually indicates which of the 3 orbitals it is. Is it the first one, the second one, or the third one? Is it minus 1, 0, or plus 1? So that's P. Once we get to D, what are my different? So I've got a D subshell. What are my values for M to the L when it's a D subshell? That is correct, Ryan. So I want to tell me what's on the chat.
-2, -1, 0, 1, and 2.
Yep. Because D, the subshell
5.
number for D, it's the third one, and we start at 0. So it's 0, 1, 2. So it's 2. And so for orbitals, how many orbitals does it have? Well, since its subshell is 2, we start at minus 2, and then we go minus 1, 0, plus 1, plus 2. And the same thing holds true for D. If we were to write an orbital diagram for our D subshell, it would have 1, 2, 3, 4, 5 orbitals in it. Put our electrons in, 1, 2, 3, 4, 5. And we call them minus 2, minus 1, 0, plus 1, and plus 2. Okay? Now, last one. F, the big subshell. How many different values for M to the L describing the orbitals in that one? And Ferris and Ryan, you guys are quick today. So I have an F subshell. What are my potential values of M to the L? Oh, yes, Ferris, go ahead.
So I'm kind of understanding it. I'm just trying to understand more of the whole S thing. Is that the only one that the whole negative L through positive L doesn't really apply? Because like -0.
Right,
0,
exactly. That's why S is given the subshell number of 0, because there's only one orbital in it. And so you can't use the rule minus L to plus L. That works for everybody but S. Okay. So that's why it's there. That's why we give it the number 0, to sort of remind you that that's unique. S doesn't have any other minus or plus. It's not adding any additional orbitals. It only has the one. And so the address for that single orbital is 0. Every subshell has a 0 orbital, but with S, that's the only one it has. But as you saw, P has 1, D has 1, and F is going to have 1 too. So what are my potential values for M to the L when I have an F orbital? So its value of L is 3. So what's the
negative? Oh.
Yep, go ahead.
-3.
Yep.
3.
What's next?
Oh, -2. -1,
Yep.
0,
Yep.
1, 2, and
Nope.
3.
You always put a plus. Always try and put
Oh,
a plus
okay.
there.
Okay. So +1, +2, and then +3.
Right. So how many total orbitals is that?
7.
7. Yeah. So that's why you know that it only occurred to me, like, you know, when I first started teaching this, that's how you can figure out how many orbitals there are, because it's been so long since I looked at this, and whoever explained it to me long ago, either I forgot it or they weren't very good at it. I probably forgot it. But why I like to sort of teach it this way is because if you ever forget how many orbitals there are in a subshell, this will show you. It's a quick and dirty way to figure out how many there are. And it also explains what the address for each one of them is. So yeah, there's 1, 2, 3, 4, 5, 6, 7 places, 7 little houses I can put my electrons in, and there's room for 2 electrons in each one. So F can hold 14 electrons. There's 7 places to put them. So at the end of the day, the answer to the first one, N, remember, can be 0. Oh, sorry. Look at me already screwing it up. Can be 1 to 7. Okay. L can be 0 to 3. M to the L, the maximum value it can have is -3 out to +3. Those are the possible values. And what we didn't do is, what are the possible values of M to the S? How many different values can it have?
2.
Just 2. That's right, because this is a shell, this is a subshell inside of it, this is an orbital inside the subshell, and there's finally we get to the electron. That's the actual address of one electron. Because remember, the 4 quantum numbers are unique for every single electron. So by the time you get to the last one, we're talking about 1 electron. So it can only be 2 values because it can only be 2 electrons in a particular place. So what are our values for M to the S?
Positive and negative?
Positive and negative what? You're right, it's positive and negative. What number?
I see in the book 1/2, -1/2, and +1/2.
Yeah, yeah, +1/2 first. And then, so that's the very first electron. So when we have an orbital, the very first one we put in there, we say we have the arrow pointing up, and we say that its spin number is +1/2. The second electron that goes in, it's pointing down, and we say that its spin number is half, -1/2. So there's only 2 possible values for M to the S. Oh, and Ryan, M stands for magnetic. That's what M stands for. Yeah, so since there can only be 2 electrons in a particular address, there can only be 2 values for its spin. It's either spinning in one direction or it's spinning in the other direction, and that's it. So there's 7 possibilities for N. There's 4 possibilities for L, 7 possibilities for M to the L, but then there's only 2 possibilities for M to the S. Yes, Nicholas.
For M to the S, is there another reason besides that it adds up to 1 that we use halves?
I think it's just to differentiate it from all the other numbers.
Okay.
I think that's the reason. I mean, I wasn't around when they came up with it, but I think just so you don't confuse it with all the others.
Okay.
So, because when you give basically you'll know when you're finished a complete set of quantum numbers, because the last one will look different than the others. I guess, I don't know.
I think
Yeah, it could have easily been, -1 and +1, but
And I guess that equals
there's a 50% chance to be spin positivity, and
yeah,
oh,
maybe.
that makes sense.
Yeah, maybe. When you add them together, there's comes to 0, which would be the net spin. But the same would have been true if it was 1 and -1. I think it's just to differentiate it from the other numbers.
Okay.
But if you want to look that up and give a full report to the class on Tuesday, please feel free to do so. Okay, so what one would people like to do next?
I kind of want to be like more familiar with it. So can we do 2 if that's okay?
It's always okay.
Cool, thanks.
Okay, so now we're talking about subshells. So remember what our subshells are: S, P, D, and F. So name the subshells described. And so when we're writing our electron configurations, we're going to use things like this, 4s2, 6p6, 3d10, things like that. So the first number, n, always refers to the shell. How far from the nucleus is it? And then the second one, L, always refers to the subshell. What shape is it in? Is it circular, or is it spherical? Is it a single 2-lobed thing? Is it a 4-lobed thing? Is it an 8-lobed thing? You get these really weird shapes as they get bigger and bigger. So 2A, if n equals 3, what principal energy level is that? What shell is that?
Is that the third shell?
Yep, that's not a hard question. That's not a trick. That's 3. It's the third shell. And remember, when we're giving the electron configuration, we say which shell, which subshell, and how many electrons are there. So we just start with it's 3. So when any electron configuration, the first number is always what shell it's in. The second one would be what subshell, and we give a letter for that in the configuration. So if L equals 0, which subshell is that? Remember, it's either going to be S, P, D, or F.
S.
That's S. We're talking about the 3s subshell. How many electrons can I put in there?
Wait, how do you find that number again? Is that the spin?
No, it's not the spin. That is the, I think it's referred to as the angular magnetic, or the angular number. It's L. So it tells you which subshell is it. So the first number, N, is the shell. The second number, L, is the subshell. The third number is the specific orbital inside that subshell. And then the fourth number is the spin. So here we've got 2 numbers, the first 2 numbers. So we're talking about the shell, or the principal level. And then the second one is which subshell is that. And remember, it can be 0, 1, 2, or 3. There's only 4 subshells right here, S, P, D, and F. There's only those 4. So if it's 0, that's got to be the first one, because it goes from 0 to 3. So 0 says S. So we would have 3s. How many electrons can I put in the 3s subshell?
no enough information.
No, you have enough information for that.
2.
2, exactly. So next would either be 1 or 3s2. Those are the only possible values it can have. Either there's 1 electron in there, or there's 2. We don't write it if there's none. We just leave it blank. So it's either got 1 in there, or it's got 2.
But you don't know whether it's 1 or 2.
Right, we don't know. I'm just saying how many could there be in there.
Oh,
And
okay.
the answer is 2. All right, let's do the second one.
Wait, I'm sorry.
Oh, go ahead.
I'm still kind of confused. How do you know how many total electrons there could be?
How many, because we go on how many orbitals are there inside of it. And with S, there's only one. There's only a single orbital in there. Remember, the number of orbitals is minus L to plus L. And since L is 0, there's only one. We can't, there's no minus 0 and plus 0. So there's only one place it can be. That would be the 0 orbital. And in the 0 orbital, we can put either 1 or 2 electrons at the most. So the most electrons that this subshell can have is 2. Okay?
Okay.
I'm going to leave the minus L to plus L up there. It will help us. Okay, so what about the second one?
Professor?
Yes.
So if we by any chance get something like this on the exam,
You think you're going to get something like this on the exam?
probably, but
Probably.
write like the possible number of electrons like you wrote out.
If I asked it,
Okay.
notice here it's not asked. I'm just asking you now.
Okay.
If I asked it, like how many, you would put 3s and then 2 electrons. This would be the total number possible. So our second one, so n equals 3. So what shell is that?
Sure.
Third, again, the first one isn't brain surgery. The second one is trickier. But n equals 3, always, that's what we just start with. We start with 3. So that's going to be 3. Now, this time, L is equal to 1. So which subshell is that?
P.
P, that's right. It's 3p. So how many electrons could possibly fit into a 3p subshell? What's the maximum number? Yep, Jovan, yes. So how many can we put in a 3p subshell?
6.
6. And if you forget how, so the maximum number would be 6. So it could be 1, 2, 3, 4, 5, or 6. How do we get there? Well, let's look at the number for L will tell you how to get there. Because L gives you 2 bits of information, actually. It tells you which subshell is it. In this instance, it's P. So we go 0, 1, 2, 3. Special puppies deserve food, S, P, D, F. So that's P. It also, the L quantum number, also tells you how many orbitals there are. How does it do that? Well, remember, the number of orbitals is minus L to plus L. And so it's minus 1, 0, plus 1, or 1, 2, 3. There's 3 places to put electrons, 3 different orbitals. And we know that we can put a maximum of 2 in each one. So 3 times 2 is 6. So that's why I like to push that minus L to plus L, because it immediately answers the rest of your questions about, I can't memorize how many electrons are in each one. This is too confusing. Just remember, the second number gives you a lot of information. It gives you gives away the whole thing. It tells you which subshell you're dealing with, and it tells you how many orbitals are in it. Both. It gives you both those pieces of information. So let's look at the third one here.
Professor?
Yes.
I hope this is not going too far off course, but say we're in.
I hope it is. Let's go somewhere weird. Yeah.
If we're in the first subshell and we only have 5 electrons, so that's when it's gonna pull other
Can't
electrons.
have 5 electrons in the first shell. There's only room for 2.
I guess it's not when the electrons don't fill up the orbitals. Is that when it's gonna steal other electrons from something else by it to fill up?
It depends. That's a really good point. That depends how many there are. If you need another 5 electrons to fill, and we'll get into this today, and we talked about it a little bit in the lecture this morning. If you need 5 more electrons to fill the second shell, it's more likely you're going to give those 3 away and become a positive ion than it is for you to steal 5 electrons from somebody else and get a -5 charge.
Just because
one of those 2 things is easier to do.
Okay, got it.
Yeah.
Okay.
So like aluminum, for instance, aluminum has 3 electrons in its outermost shell. I think. And so it's easier for aluminum to lose all 3 electrons in its outermost shell and get a +3 charge than it is for it to try and steal 5 electrons from other elements. And we'll learn that it's basically impossible for it to do, because it doesn't have the pulling capacity to pull electrons away from other elements that something like fluorine or chlorine or oxygen does. Those 3 elements can pull electrons from pretty much anybody, but metals don't have that ability. And we're going to get into that a little bit later. But yeah, really good question. So third one, N is equal to C. So we're going to have a completely different shell this time, right? Which shell is that?
D.
No, shell, first number. D is a subshell. Third, again, third.
That one's easy. That's fun.
Now, give me, yes, D, you were right. That is a D subshell. So we go 0, 1, 2, and then 3. That is their L values. So if it's 2, that means it's a D subshell. How many electrons can I put in a 3D subshell?
10.
10. Very good. That's right, 10. And why? Well, we go back to our formula of -L to +L. Since L is now 2, we start at -2. So we have -2, -1, 0, +1, +2. That describes 5 different orbitals. The address for each one is -2, -1, 0, +1, +2. So there's 5 of them. Each one can hold 2 for a total of 10. Very good. And then the last one, number D, what do we have there?
5s.
It's 5. Man, you got that quickly. Yeah, so N is 5, so 5, it's in the 5th shell. That's the super easy one to do. So it's 5. And L is 0 again, which it was for the first one, so it's also S. And just because it's in the 5th level doesn't mean it's can hold more electrons. Just because it's bigger, and it is bigger when you think about it, because the first shell will be about this size relatively, and then the second one is this size, and then it's this size, and then it's this size. They get really, really big, but there's still only room for 2 electrons in it. So the 5s can be either 5s1 or 5s2. Those are the only 2 values. So it doesn't matter in which energy level or which shell these orbitals are. They're always going to be the same shape, and you can put the same number in them. Okay? All right, so what would folks like to do next?
For number 4, what does it mean, the destinations that are theoretically possible?
I borrowed that question from somebody. I went number 4. Yeah, it's just, I don't know. Basically, it's the ones that we have there's only, we haven't talked about like G, H, and I. I mean, yeah, theoretically they're possible, but they don't really exist. So which ones, I should have changed that to circle all the subshells that are possible and just left it at that. So let's just go through. So the first one, is that possible? can we
Sure.
have a 7s subshell?
Sure.
Yeah. Oops, wait a minute. Yeah, that works. Let's go back. Damn it. Yep, here we go.
So the 7 is referring to the n, the
Yep.
number.
Yep. So that's the 7th level. That's the furthest one away. And it has an S subshell like anybody else. What about the next one? 1p. Is that possible?
Now, I don't think it's possible
How come?
because B only have S in it. I mean, one have only S in it.
Exactly. That's right. It can only have S. So there's no such thing as 1p. There's no 1p. There's no 1d. There's no 1f. The only subshell you find in 1 is S, and that's it. You're done. And if you ever wonder that, or a periodic table, and notice the very first row is only 2 elements. Hydrogen on one side and helium all the way on the other. And that's it. There's no more. So that's the first energy level. That's the first shell. And there's only 2 elements in there. And so S is the only place you can put electrons in there. And then once you've put 2 in there, you're done. And then you move to the second level. So let's look at 5D. Is that possible?
Yeah.
Yeah. So once you've passed level 4, once you've passed shell number 4, all of the subshells are available. So with 5 can be S, P, D, or F, any of them. And so, yes, 5D works. What about 2D? Can we see a 2D subshell?
Professor, I have a question.
Yes.
So n, the shell n, 1 correlates to S, 2 correlates to P, 3 correlates to D, and 4 correlates to F?
Nope. N refers to which shell it is. So basically, how far from the nucleus is it? So it's either going to be shell number 1, shell number 2, shell number 3, all the way out to 7. That basically just says in, which period of elements am I dealing with? The first one, the second one, the third one, the fourth one, the fifth one. And so it just says basically which energy level that we're going to put all the electrons in. Is it the first one, the second, the third, or the fourth? It's the second quantum number, L, that tells you what subshell we're dealing with. That is either S, P, D, or F. This tells you the shape. The first number, N, tells you how far you are from the nucleus. It's the second one, the S, P, D, and F, that tells you what shape it is. Okay?
So, sorry.
Oh, go ahead.
So then how does 5 indicate, or say if it was 4D on letter C, then how
Okay.
do we?
How do you know whether it's possible or not?
Yeah.
Good question. Because the value of L, the maximum value of L is n minus 1. That's the maximum number, the maximum value for L. So if I'm at 1, the maximum value of L can be is 0. So that tells me I can only have one S. That's it. That's the only one I can have. If, on the other hand, if n equals 2, then L can either equal 0 or 1. Those are the two values it can have. And since it's 0 and 1, 2 can have either S or and P. You can have both of those. And then when n equals 3, the values of L can be 0, 1, or 2. So that means S, P, or D. Every time we add another shell, another level, we add another, there's room for another subshell to go in. So by the time we get to 4, we have all 4 subshells possible.
So that equation is better to use to kind of get a grasp on it. N-1, and that'll give me.
N-1 is the maximum. Yeah, I may not have. Yeah, that's probably a really good point. I may not have pointed that out well enough.
Oh, you probably did. I'm just trying to.
I can't remember, but yeah, that's the maximum value that L can have. So that tells you how many subshells are possible. So in 1, it's 1. In 2, it's 2. And in 3, it's 3. And in 4, it's 4. And so it tells you how many subshells there can be. So here, I'll ask you right now. So with 2D, is that possible? Think about what value of L, what value of L it is for D.
I would say no, because N minus, so 2 minus 1 is 1, and that would only give me either S or P.
That's exactly right. Very good. Yeah, that's exactly right. So because their principal energy level, or a shell, same thing, is 2, my maximum value of L could be either 0 or 1. I can't get any higher than 1. And so it's either going to be 2s or 2p. That's it. It can't be anything else. So I can't have a 2d orbital. What about 4f? Is that a possibility?
Yes, it's possible.
Yeah, how come?
I can find the same rule on -1, I believe.
Mm-hmm.
Yeah, but yeah, I know D is up to 3 and F up to 4 too.
Yeah, right. So if I take my L is maximum value is N-1, and N is 4, the maximum value of L is 3. And so I can have either 0, 1, 2, or 3. The other way to think about it is if there's 4 subshells. So by the time I get to shell number 4, they're all available. So anything 4 or larger has all 4 subshells available. So once I get past 3, any of them are available. S, P, D, or F are all present in all shells 4 or higher. And then this 5G, yeah, theoretically, I mean, we can go past F and go to G, H, and I, but I mean, I won't ask a question like that on a test. That was, because yes, it is theoretically possible, but it's not something we've talked about. So you're not going to find it on the periodic table. So I think what I would do is just what subshell destinations that are possible on the periodic table and leave it at that. Because there isn't a place in the periodic table where you will find an element that has a 5G subshell. So yeah, theoretically, it is possible, but we haven't talked about it, and there's no place in the periodic table for it. So let's not think about it, shall we? Let's not make it more complicated than it needs to be. Okay. All right, what do people like to look at next? Number 6. Everyone wants to look at number 6. Okay. Or everyone, 2 people. Now, the Pauli exclusion principle. Anyone remember what the Pauli exclusion principle was? Now, we had a lot of rules this morning.
I'm just reading this from the book.
Someone's reading the book. I love it.
No 2 electrons in the same atom can have exactly the same set of all 4 quantum numbers.
Right. Right. It basically means you can't put more than 2 electrons in an orbital, because if you do, so remember, oh, damn it. here we go. In each orbital, so I make my little house. In each orbital is only room for 2 electrons. So if I put in 1, that gets the final spin quantum number of plus 1/2. Now if I put in 2, that gets the negative 1/2. So if I put in a third one, there's no room for it, and there's no number to describe it. So basically what Pauli's saying is that you can't have more than 2 electrons in an orbital. There's only room for 2. So if we look at these, some of these break that rule, and some of them don't. So let's look at A.
Seems it's breaking the rules with the 2b7.
That's right. How come?
2b is supposed to have 6 electrons, and over here it's having 7. So
Exactly. There's only
I
room
think
for
it
6.
would be-
So if I make a P subshell, this is -1, 0, and +1. 1, 2, 3, 4, 5, 6. There's only room for 6. There ain't room for no more. So we can't have 7 in a p orbital. That doesn't work. Excellent. All right, what about the second one?
Looks
there
pretty
shouldn't
fine.
be-
What is it? Somebody had it. Go ahead.
There shouldn't be 3 electrons in the S.
That's right. That's right. Because S, this is basically, we're looking at an S orbital here. There's only 1 orbital in an S subshell, and there's only room for 2. There's no room for this third one. And so this doesn't work. Excellent. What about the third one?
Yeah, orbital D, I think, only can have 10 electrons because we have 5 orbital in it.
That's right. Yeah,
Or
D,
subshell
there's a
size.
problem with D. Because D, L for D is 2. And so the possible number of orbitals in there is -2, -1, 0, +1, +2. That's 5. And we can only put 2 electrons in each one, so 12. It's not going to work. Excellent. What about the last one, D?
It looks good.
Yeah, that's fine. There's no problems with that one. All the S orbitals, all the S subshells have 2 electrons in them. The P orbitals have 6 in them, so we're
Excuse
good.
me.
Yes.
Do we write like this, or do you like write like 1s to the squared and
Yeah, it
to
would be
S?
to be a superscript. Yes. It would look like, yeah. That's just what happens when you move something from one Word document to another one. Sometimes the subscripts move down.
Okay.
Professor, this is like a question I probably should have asked like 2 or 3 weeks ago. But
Okay.
if the electrons are negative, how are they in the same orbit?
That's a really good point. That is why, man, that's a fantastic question. Let's get a,
I think my
whiteboard.
explanation would be the nucleus is positive
Right.
charged. And
Yes,
that's
well, we
will
know
have-
why the electrons are sort of circling the nucleus
Yes.
at the same charge. But the question is, how come they come together in the same location? And that answer is they don't really. They now what happens is, yeah, so when we think about what these orbitals look like, if you remember, the p orbital kind of looked like this, right? So that was one of the p orbitals, and then this was another one. And then the third one was going backwards and then coming out at us. So we draw them like this, 1, 2, 3, 4, 5, 6. So it's like, oh my God, they're like, stuck together in the same place. They're not. Realistically, one electron would be over here and the other one would be over there. One electron would be here and the other one would be there. They'd be separated in space from each other, but they're considered to be in the same orbital. Okay?
Okay, and are they equally separated between all of them?
Yeah, I mean, they're all negatively charged. So to reduce the repulsion, and this is really important when we get into talking about the shapes of these things. When we're dealing with the repulsion of these electrons from each other, because they're the same charge, shapes the molecules as well. So that's why, and I'm going back to these p orbitals, that's why the p orbitals are all at 90-degree angles to each other.
Oh, okay.
Because that maximizes the distance between all of them. So if I have a pair here and a pair there and a pair there and a pair there and another one going this way, another one going that way, by putting them at 90-degree angles, that's the maximum distance they can be from each other. If I increase the angle at all, it then starts to interfere with another pair of electrons. If I shorten the angle, then these two pairs of electrons start to come in contact with each other. So it's at 90 degrees where they exactly have the maximum distance from each other.
And this might be getting a little bit into calc, but if we took an exact instance of time, is the electrons, are they like evenly away from the nodes, like a pair of electrons?
Well, that's the difference. That's one of the differences between classical, or sort of, Isaac Newton physics, and quantum mechanics, is that all of these things are probabilities. So when I say that this is what a p orbital looks like, I can't say that the electron is here, or it's there, or it's here, or it's there. There's no way of knowing. All you can know is that the probabilities are the highest here and the lowest there. And that's pretty much all you can say.
Okay.
You can't nail it down specifically. That's part of what the Heisenberg uncertainty principle is. You can measure how fast an electron, you can measure the velocity of electron accurately, but then you can't tell where it is. You can sort of try and locate the location, try and nail down the location of an electron, but then you're uncertain about its speed. So there's always going to be some uncertainty here. So these are just probabilities. All these shapes are just probability functions. That's what a wave equation is. It's a probability function. It says, where in space am I most likely to find this thing? And in a p orbital, well, I'm most likely to find it along this shape right here.
And I think that's what I was kind of getting at, like the tangent line of the wave. I think that
You're exploding my head now, bro. You've pretty much got to the limit of my theoretical physics experience.
Okay.
But yeah,
Is there a way
we can
to
definitely
force
get
them
into
to
that.
solve?
We can definitely get into that later, because that's some really interesting stuff when you get into the real theoretical parts of this stuff. I love watching that kind of stuff on TV. Because then you get into like black holes and all that kind of stuff. But yeah, that's a little beyond this class. Okay, what kind of question would you like to look at next? Unless you want to like break down some wave equations.
We cannot see the screen. I mean, the screen is small for us.
Oh, right. I need to. Okay.
And we have a question from Faris too, is number 7 and the same principle.
So you still can't see the?
No. So we have 2 slides, small ones.
Oh, here we go. Okay. What about now?
That works.
Okay.
Yeah.
All right. Yeah. So 7, basically, 7 for all intents and purposes, it's the same question. Yeah. That's basically the same question. And then just explain why each one. So what about, 8? That's fun. So 8, you actually need to have the periodic table in front of you. It's basically going to be impossible without a periodic table. B you should be able to figure out without a periodic table. What would be an atom with a completely filled outer shell?
Would it be the s orbital?
No, an atom. An atom. Give me an example of an atom that has a completely filled outer shell. What atom? There's
Noble
a special family of those.
Noble gases.
Any of the noble gases. That's right. So helium. Oops. Where are we? Helium has a completely filled first shell. And then neon has a completely filled second shell. And then argon has a completely filled third shell. And krypton has a completely filled fourth shell. They're all completely filled. And that's why they're noble gases, because they've completely filled the complement of electrons for each level. And so then there's no need to either add electrons for stability or lose electrons for stability. They're as stable as they're the most stable elements there are. And so and helium and neon and argon in particular are just super inert. Like neon doesn't even become the liquid until you get down to like 2K or like 1K in temperature.
Someone in the chat asked, is hydrogen and lithium half filled?
Yeah,
hydrogen is half filled, yes, but it doesn't have, yes, that would be a half filled subshell. That is correct.
And why is that?
Because hydrogen basically has just one electron. And so its electron configuration is 1s1. It's the smallest electron configuration. It's the shortest one, well, not the shortest. It's the smallest one there is. So it's only has the first level, the first shell. The first shell only has one subshell, and there's only room for 2 electrons. So hydrogen is half filled. Yes.
So that goes the same for sodium, potassium,
and lithium.
It's everything that's in the column 1.
What elements are those?
Half filled.
Lithium, sodium, potassium.
What elements though are they? What do we call them?
Is it
remember?
Or alkaline metals?
Alkalis, yes. Alkali metals. Yeah. You could also give there are other examples in there too. You could look, for example, there is a whole group of nonmetals that are also have half-filled subshells.
Nitrogen.
Yeah, so why nitrogen? How many electrons does nitrogen
Because
have?
the outer field 7.
So nitrogen has 7 electrons. So it would go 1s, 2, 2s, 2, 2p, 3. And we know that p has 6 in it. So that's half filled. That's also an answer for C as well. So nitrogen has a full subshell. The first subshell, actually, no, when you look at it, no, it has a half-shelled orbital. No, subshell, no, that's right. Yeah. Doesn't say filled shell. So a half-filled subshell would be S, P, D, or F. Yeah. So if that's the case, how many electrons do you need to have a half-filled P subshell?
7.
No, just in the subshell itself. So if P contains 6, has room for 6 electrons, how many would you need to have it to be half filled?
3.
3, right. Then what about D?
5.
5. And then F?
7.
7. Yeah, so any of those elements that ends with a P3, a D5, or an F7 will have a half-filled subshell. And I think I mentioned this morning that a half-filled subshell is a sort of quasi-stable feature, because especially with the transition metals, if you have a half-filled D subshell or a half-filled F subshell, that's fairly stable, and that the next electrons to add may not go in putting more electrons in either the D or the F. They'll go somewhere else. They'll fill a P or they'll fill an S first before they go back and add more electrons to a half-filled D or a half-filled F, because those are stable. Not as stable as having them completely filled, but pretty stable. And that leads to different charges on different elements. Okay. What do folks want to work on now? The sigh. The sigh. We can review 9. It gives us a chance to draw our diagram. Let's draw our diagram for determining the order that these come in. You remember how to do that?
Diagonals.
So on the left side, we write down N. So we go 1, 2, 3, 4, 5. And around the top, we put S, P, D, and F. And then we just write out how many subshells are in each shell. We just write them out. So when N equals 1, how many subshells can I have?
1.
1. And what do we call it?
S.
1s. Now put the 1 in there as well. And then we're done. Now what about 2? How many subshells are present in 2?
5.
5?
We have 2s and 2p.
That's it. Just 2.
Oh, just 2. Okay.
2s, and then under the p we put 2p. And then what about the third one? What's possible in 3?
3s, 3p, and 3
And 3p, is that it?
and 3d.
And 3d, right, because every time we increase an energy level, every time we increase a shell, there's room for another subshell. So we just keep adding one more. So then by the time we get to the 4th level, they're all present. So I can have 4s and 4p and 4d and 4f. And the same is true after 4. So 5, 6, and 7, we just keep the same. It's the same 4. Yep. 5p, 5d, 5f. So then the question is, well, how do we figure out which order these are filled in? And to do that, we connect them with diagonal lines, starting with 1s. So we just go on a diagonal this way. So first one, 1s. And then we come back. Second one only hits 2s. Third one hits 2p and 2s. Third one hits 3p and 4s. Next one, it's 3D, 4P, and 5S. And remember the order. The next one, 4D, 5P, and then would be 6S under that. So we just write down the order that they're falling in. And let's write down what the order is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that would be the order that we go in. Does everyone see how that works? You can either, make a table, you can print out a table or whatever. Again, you guys are lucky. You don't have to write this, you don't have to stress out during an exam and figure this out.
Yeah, that's what I was going to ask, if we have to write this.
Well, I can't stop you from making one of these and just having it. So again, as I mentioned before, I'll probably give you a harder question than just place them in the order of increasing energy. Okay. But that's how we would write it out. So the first would be 1s. What's the second one? What's number
3S.
2 there? No, number 2 is not. So 1s is first. What's the second one? Oh, well, I'm sorry, in order. Yes, in order, the order that we figured out over here.
Oh, 2S.
Yeah, 2s. And then?
And we don't have 2S here.
No, I'm just saying, what's the order?
Okay.
Yeah, that we fill these things in. And then you can use that to reorder these. So 1s, 2s, what's after that?
2P.
Mm-hmm. Yep. Keep going.
3S.
Yep.
3P. 3D. 4S.
5, 3, 3P, 4. Yep, 4S. Mm-hmm.
4P.
4S. Nope.
I'm so lost.
3D.
3D is next. Yep. That is one of those where remember, we sort of we talked this morning. Once we start to get to the higher levels, the difference in energies becomes so small that they kind of flip sometimes. And so 3D is actually slightly, or 4P is a slightly higher energy than 3D. So 3D comes next and then 4P. And then what's after that?
5S.
Mm-hmm. Keep going.
4D.
Yep.
5P.
Yep. 5P. And then down here would have been 6S. And then after 6S would have been 4F, 5D, 6P, and so on. So that's just, so you make a big diagram that has all of the 1 through 7 levels. So you have them all on there. So you can basically follow them all the way through. So then use that to put these in the right order, okay? All right, what about quantum numbers are unacceptable? I should be able to do that one. Now, yeah, I want to review this one. And because this sort of show us how we use the individual quantum numbers to show exactly which electron we're dealing with, and we have to know the order that they're put in there in order to describe it. Okay, so this first one is a 3P subshell. So we know what the first quantum number is going to be. What's the first one going to be? First one's always N, the shell number. So remember, there's 4 quantum numbers. First one is always the shell. So what shell are we dealing with?
The third one.
3, exactly. Next is the subshell. So, or L. So the first one is N, the next one is L, and then M to the L, and then M to the S. So the first one is the shell. Second one is the subshell. Which subshell are we dealing with?
Two.
What is it?
2.
2. Okay, so if my second quantum number is 2, what subshell is that referring to?
D.
That's referring to D, that's right. Because
Oh,
S is 0, P is 1, D is 2, and F is 3. So 2 would be a D subshell, and that's not what I have, right? So what's the proper second quantum number for this electron?
1.
1, right. That would be 1. What about the third? Which orbital is it? How do we figure that out?
+1.
Right, +1. M to the L goes from -1, 0, and +1. And that's the names of each of those individual. That's what I want you to remember. That's the name, that's the address for each one of these orbitals. So it's -1, 0, and +1. So this third one is +1. So we would put +1. And then what's the last number?
+1/2.
Right, exactly. Now, so those would be the 3 or the 4 quantum numbers for that specific electron. So here's a curveball question. What number electron was that going into that subshell? Was it the first, second, third, fourth, or fifth one? And yes, you should be able to determine that.
The third,
The third, excellent. Why the third?
because you go one by one. So the first orbital, second orbital, third orbital with the one you want, and then
Excellent, that's right. Because electrons repel each other. So they will be separated as far as they possibly can be in space. And therefore, they fill these one at a time. So the third one in is always going to be pointing up, because it's doesn't go in the first one, second one goes in the, so first one goes in -1, second one goes in 0, third one goes in +1, all pointing up. And then the fourth one back to -1, pointing down. The fifth one pointing down at 0, and then the sixth one would be pointing down in +1. Excellent job.
is that the Pauli exclusion principle?
Mm-hmm. Yeah, and the Hund's rule,
Okay.
where you go into the lowest energy state first. And so it's a lower energy state being by yourself than being, put in with another. So first you spread out as much as possible and then start adding some more. Right, so 3, 1,
Does
+1,
Hund
+1/2. Go ahead.
does Hund mean dog in German?
Mm-hmm. Yep, I've got 2 Huns. Well, they're both, one of them snoozing. Hey, Candy. Yeah, luckily we haven't had any motorcycles go by today, so you haven't heard the Huns. All right, so let's do C. Who wants to do C for me? What do I start with? Oh, sorry. N, L, M to the L, M to the S. So for this third one, what's my N?
4.
4. Excellent. 4. What is my L?
2.
2. So S, P, D, 0, 1, 2. Right, so 2. Which orbital is that bold electron in? What address do we give to that particular orbital, the very first one? Because we're talking about this one here. Remember how we get m to the L numbers? We go from minus L out to plus L. And it's in the very first one. So if my L is equal to 2, what would be the very first value of m to the L?
-2.
That's right. Excellent. -2, -1, 0, +1, +2. And that's why I say every single subshell has a 0 orbital. They all do, because they all have at least that one. And then we just keep adding a pair at a time. We add a -1 and a +1, a -2 and a +2, a -3 and a +3. But they all have 0. So they all have that as the base. And then we just keep adding one on either side. So what's my m to the L for the 4D subshell there? I got 4, 2. What's my third number? M to the L. You just told me.
-2.
Yep. -2. And what's the last number? The spin. Last number is always the spin. It's pointing down.
-1/2.
Yes. You had a 50-50 shot at it and you nailed it. Yeah, -1/2. So which electron was this going in? Was it the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, or 10th?
6.
Right. 6th one in. First 5 are all in separate houses, all pointing up. 6th one goes into -2, and it's the first one to point down. Excellent. So I'll let you do and so getting back to magnetism, this particular element right here, notice that it has 4 electrons all pointing up. And this pair is the only one that's paired off. This element would be very magnetic because it has a lot of electrons all pointing, all aligned, basically pointing in the same direction. I think, where are we? Iron. Where the hell is iron? I think iron has 4. Yeah, iron has 4 electrons all pointing in the same direction. So this actually could be iron when I think about it. Yeah.
Iron is 3d6.
Yeah. So it has, just like this. So it has 4 electrons all pointing in the same direction. And explains why it's so magnetic. Okay. Now I think I'll do one of the last 2 with you guys. Because we didn't talk about what a noble gas configuration is. Now, a noble gas configuration basically skips all of the, it skips all the 1s1, 1s2, and 2s2, because when we're dealing with these big elements, and Mercury's big, Mercury is 80. Mercury has 80, oops, go back. Mercury has 80 electrons. It's a lot of electrons. So if we had to write out the electron configuration of the whole thing, it would take a really, really long time. So basically, when we get to these big elements, what we do to shorten it is we go to the next smallest noble gas and just write what that is in brackets. So for instance, for sodium has, how many electrons does sodium have?
11.
Has 11. What is the next smallest noble gas to sodium?
Neon.
Neon.
Neon. Neon has how many?
10.
10.
So what we do, we put in square brackets, neon, and then we would give the address or the electron configuration for only the one additional electron. And for sodium, that would be 3s1. And then we're done. So you can see that this is a lot quicker than writing out the whole thing. And it basically gives us an idea of what are its valence electrons. Well, 3s1, there you go. Tells you what level it's in, tells you what subshell it's in, what orbital, all that good stuff. So there's one. So this pretty much explains why sodium gives away this particular electron, so it can have the electron configuration of neon and be super, super stable. That's why sodium ions with 10 electrons are so stable. They're super stable. So when you throw sodium in water, it goes from being an unstable metal to being a very stable ion. And that's why it reacts so violently. So when we have 80 electrons, that's a lot more. So what is the next smallest element or noble gas has less than 80 electrons?
Xenon.
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 And how many electrons does xenon have?
54.
54. So for mercury, we would say, oops, xenon. And that's our first 54 electrons taken care of. And then you just go to the periodic table and then go over. And so the next element is cesium. And then you just go down 1, 2, 3, 4, 5, 6. 6s2. And you just keep going. And you just, as you follow along, you fill out the periodic table until you get to 80 electrons. So you would need to add another 26 electrons. So you can do it one of two ways. Either you can refer to your table that you made with your S, your P, your D, and your F, and your 1, 2, 3, 4, 5, 6, 7. Do it that way. Or you can go to the periodic table and just read across. You can do it that way as well. Yeah, it would help if we had the periodic table all together, but we don't. So let's let's do the periodic table way. You guys can also, when you're doing it at home, do it using this method, if you like. But using the periodic table, let's have a look. So it's kind of hard to zoom in here. So cesium and barium are 6 down. I might as well just write the numbers down here for you to be able to see. So 1, 2, 3, 4, 5, 6, 7. So you can see we're at number 6, and this is my S block here. So 1, S block, 1, this is hard, 1, 2. So that's my first 2. Actually, why don't I just pull up instead of trying to do this, I can just pull up the actual table. Let me see if I can find it. No, this isn't working. Damn it. Okay, I'm just going to stop sharing for a minute. Oh, I can't minimize. Oh, here we go. There we go. Did everyone see the table now? Whew. This might be easier. Everyone see the periodic table?
Yeah.
Yes.
Okay. Yeah, this is the one I put up today. So hopefully this will help. So I dropped my pen. So this is so easy to do remotely, isn't it? Where's my annotation? There we go. Okay. So here is Mercury over here. So I want to go from xenon, which is here, all the way through to Mercury. So I start, xenon is 54, and then I have 55, 56, and those are in the S block. So that would be 1, 2, 3, 4, 5, 6, 7. So that's 6s2, right? And then next comes an F block. F block is down here. Here's our F block. These are the lanthanides here. And they go from 57 to 71. And that would be 5 or 4. 1, 2, 3, 4. I think 4D. No, I'm sorry, 4F. I think it's 4F. That's why it would help to have the arrows there. So here we have an F block. And I think it's 4F, 14. And that takes us to 72. That takes us to here. Now we're dealing with a D block of 10. So we go across 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that takes us, so 4F14, 5D9. No. Yeah. Does that work? Oh, wait, I have 10. Did I leave one out? 1, 2, 3, 4, 5, 8, 9. Oh, right, there's 15 there. So that's 10. So yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. FD10. So I know it's a little bit confusing. I'll try and do a better job going over it. You may do better using your arrow diagrams than looking at this. But so 54, and then 6s2. These are our 2 s's, and then we have. That's why it's confusing having this pulled out. When it's put back in, it makes more sense. So those are our 6s2, and then we go to 4f14, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5d10. So at the end of the day, 6s2, 4f14, 5d10. So let me go back. Yes, it's painful. Oh, wait a minute. All right, so got rid of my mercury, unfortunately. Right, so the noble gas shorthand is, we start with xenon that has 54 electrons, and we have to add another 26 electrons to get to 80. So mercury has 80 electrons. So remember, we go down to 6, level 6, and then we go across 2 S's, so 6s2, and then we go across 14 F's, 4f, 14, and we went across 10 D's, 5d, 10. And then just count up the electrons. 2 plus 14 plus 10, 26. So that's the shorthand for xenon. What's the next smallest noble gas? And then go from there. So
How did you get 4F for
it's the first set of F. It's the first F block.
okay.
And so the very first time F shows up is in the 4th level.
Okay.
Yeah. And then it's the 5th D after that. And then so you have a total of 26. Or, like I said, just make your diagram, 1, 2, 3, 4, and you see the order there. It'll give you the complete order, and then you just follow that until you get all the electrons placed in there, okay? So the orbital diagram, we're actually going to need every single electron to figure that out. Or we could, let's just do the whole darn thing. So the orbital diagram for Mercury. So here we would actually need the complete electron configuration, all 80 electrons. So let's get the order.
Would that be super long?
Mm-hmm. So so on a test, I might just ask for like either the complete orbital diagram or just the orbital diagram of these. So I don't know, probably just here it just says the whole thing. So probably the last, give all of the electrons, starting from 1s all the way out to 6s2. So just refer to the order of the filling order that we've done there. And then the quantum numbers of the 80th electron. So which level is it in? Which or subshell is it in? Which orbital is it in? Is it the first one in for +1 or the second one in for a -1? Would you like to see? Should we just do the whole thing? And then
For part B, it's the full configuration that we're writing.
Yeah, this is kind of I should just change that to the orbital diagrams for the second set of letters, the second set of electrons, because it's kind of stupid to write out the shorthand electron configuration and then basically have to refer to the complete electron configuration. But yeah, why don't we just do that? Just because we'll have plenty of practice doing shorter electron configurations. Yeah, just the orbital diagram of just these. Have them in the right order, the right energy order. Okay?
Okay.
Okay.
And then the last one is, now this is going to be different because we're not dealing with an element. So what are we dealing with here?
Electron.
Yeah, we're always dealing with electrons. But what's the electron configuration? What have you been asked to write the electron configuration of?
A polyatomic ion?
Nope. I only see one element there. I just see S. So it's not polyatomic.
Shoot. Is it one of the ones that like hydrogen has to have 2 and oxygen has to have 2?
When you say oxygen has to have 2.
Like O2 in when you find it in nature, it's O2. Is that like the same thing that we're talking about?
Well, sulfur is lowest. This is sulfur. S is for sulfur, right? Actually, the lowest energy configuration of sulfur is S8 for some strange reason. So it isn't S2 in nature. It isn't a gas. It's a solid.
The diatomic is.
It's not a diatomic. So what is this? I'm just asking you, what is that?
Sulfide.
Sulfide ion, right? It's sulfide ion. So it's not sulfur. That would be sulfur. This is sulfide ion. How many electrons does sulfide ion have?
10. Is it 8 plus 2?
There's more than that. Oxide ion is 10.
16 plus 2.
That's right. Sulfur has 16 electrons. Sulfide has how many?
18.
18. So sulfide ion has 18 electrons. So that will throw you off, like in a test or something like that. If you give the orbital diagram or the electron configuration of sulfur, that's incorrect, because this isn't sulfur. It's sulfide ion. So it has 2 more electrons. So basically now we would give the electron configuration of sulfur ide. So 2 more. So you have to have 18 electrons to get this one correct. So it's a bit of a trick question here. The noble gas shorthand would not be what you think. So what's the what would be the electron what's the closest
Would it just be
noble
argon?
gas?
Would it just be argon?
You would think, right? I've seen it both
Neon?
ways. I've seen it written as argon, and I've also I've more often seen it written as neon plus 8 additional electrons to sort of really make the point that it has a full configuration, because it in contrast to sulfur itself would be neon plus 6 more electrons. So you could do it either way, but I normally see this one more frequently.
So we're going
Either
off
one is correct.
So we're going off I guess for lack of a better term, the regular sulfur, and that's why we're using neon and not argon.
Right.
Okay.
Exactly. It's to compare it more directly to the sulfur atom. Exactly. So we would put neon, and then what would be, so after neon, what would our next 2 electrons be? This really helps to have a periodic table in front of you.
3s2.
3s2, right. So the next is sodium at 11, and then magnesium at 12. So those are our S block, and they're in the 3rd row. So it would be neon plus 3s2. And then we move across the periodic table, and also in the 3rd level, and we come to the P block. So it would be 3p, and then we just go across until we get to sulfur, and then add 2 more electrons. So how many more electrons do we need? So we have 10 here, and we need 8 more. So we have 3s2 and then 3p.
3p6.
6, right. So that gives us our last 8 electrons. So 10 here, 2 here, 6 there for a total of 18. And that's sulfide ion. So before we go, let's just quickly show how we would write that in an orbital diagram. So remember, the orbital diagram shows each individual box for the orbitals. So we would start, and we need 18. And we always start with 1s, and then 2s, and then 2p, and then 3s, and then 3p. So 1s, 2s, 2p, 3s, 3p. Well, I should make my p a little bit bigger here. Let's do that. Okay. So what's the first electron I put in? Where do I put my very first electron?
It's an arrow, an up arrow, and that's plus half.
Put it in 1s, right?
Mm-hmm.
So the first one will go there, and the second one?
Will go down.
Arrow down.
Same 1s.
Same one. Then what about the next one?
2s.
Up. And
Down.
then?
And 1 down.
Now what about 2p? How do I put them in there?
3 ups, then 3 downs.
Yep. 1, 2, 3, 4, 5, 6. So now I've got a total of 2, 8. I've got 10, and I need 8 more. So what's after 2p? What's next?
Up, down, up, down, down, down.
So 3s, 1, 2, and then 3p, 1, 2, 3, 4, 5, 6. So that gives me another 8. So that is a total of 18. Yeah. So that would be it. So the quantum number. What was the last electron put in there?
Three, comma.
So it would be this one, right? That was the last electron that was added. So that's the quantum number. I want the quantum numbers for that specific electron, okay?
Three, comma, 1, comma. Positive 1, comma. Negative half.
Mm-hmm. Yep. So any other questions? I left number 10 out. 10 you can basically answer on your own. Those are like, just basically identifying things. I figure I would go over that one. We've pretty much gone over everything else. So any other questions before we call it a day?
Just confirm. For 13B, do we write the shorthand, right?
13B. Yeah.
Okay.
Yeah. I'll make an announcement about that, but just for the folks who weren't here or left already. Yeah. Just the ones that aren't in Xenon. That would be fine. Although on a test, I might ask for the whole damn thing. So just be prepared. Actually, for one bonus question one year, I asked for the electron configuration of uranium. The entire thing. And they didn't have a sheet to work off of. So I think I got maybe 4 people out of the class who were able to get that one.
Why are they all not stacked?
Why are they what?
Why are they not stacked? Like, doesn't 3s and 3p have different energies?
Yes. So if you wanted to actually do these correctly, yeah, 2p would be slightly higher than 2s, and then 3p would be slightly higher than 3s. You're right. Yeah, I was a little lazy there. Yeah, they should be slightly higher. Not by a lot, just by a little. Because there is a higher energy. That's right.
Okay, thank you.
Professor?
But I'm not going to nail you for not doing that. But yeah, it should. Yes.
For 14C, would it be 3, 1, 1, negative 1/2 for the
You have to have a plus or a minus for the, so if you have N, L, M to the L, M to the S. Those are your 4 numbers. So N is 1 to 7, L is 0 to 3, M to the L has to have either a plus, a 0, or a minus. So it has to have either a plus or a minus or a 0 there. You can't just have 1. It has to be +1 or -1.
So
and then
my
the M to the S would be a negative 1/2 plus 1/2.
so I put 3, 1 plus 1 negative 1/2.
Right.
Okay.
Yeah, because the address here is -1, 0, +1. That's correct. Mm-hmm. Anything else before we head out?
So for Mercury,
Mm-hmm.
the F block and the D block, sorry, the D orbitals are fully occupied, right?
I believe so. Yes.
So would it be relatively stable if that is occupied?
It is relatively it is relatively stable. But remember, just because the subshells are fully occupied doesn't mean the shells are, and so
Okay.
there is still it's still chemically active.
Okay.
Yeah. But yeah, having them being leads to somewhat less chemical activity than something that wouldn't have full shells. Yeah, it still oxidizes though.
Okay.
But not as quickly as like, iron or something like that. Okay. I think we've tortured each other long enough. So if you have any questions about this, send me a note. I'll have office hours on Monday. I will have the study guide ready for you by tomorrow. And if I don't see you before then, have a good weekend, everyone. Okay?
Thank you. Have a good weekend, all.
All right. Bye-bye.
Thank you.